Alright guys, this is going to be the first video about how we came to understand magnetism. And in this video, it's not going to be highly physicsy as most people might recognize it, but I think it's really important because we need to understand that physics, that math and science in general, are not just outside of the human story as we might tend to associate them sometimes. They're not above or beyond or in a different plane, but they're very much a part, they're very much integral, and they're very much another way in which we humans take our experiences in life, in particular the ones that baffle us, and we try and better understand them, we try and better predict them, we try and better know what's going on, so we can develop a deeper connection with our world. And our study of magnetism and how we came to understand it, I think is a really good example of how this plays in with the advent of modern scientific principles. And before we get to modern scientific principles, why don't we just start out with lodestones and the ancient observations that pre-scientific people were able to make with lodestones. Now, to start, lodestones are these stones with high contents of iron ore that, due to specific conditions that were present during their formation, are magnetically charged, and they act very similarly to our modern magnets. Namely, that lodestones attracted other lodestones. And not only did they attract other lodestones, but that they actually attracted certain types of metal. And that for these types of metal, which they did attract, you could actually transfer magnetic properties to that certain type of metal. Come on. Again, not very strong, not as strong as the original magnet, but that's something. And while these magnets did attract certain types of metal, they did not attract all types of metal. This is a sheet of copper, and it is not magnetic, does not magnetically interact with a regular magnet. And it's important to note that this transfer of magnetic properties to magnetic materials actually allowed them to do an experiment that you can recreate at home if you just have a little paper clip and allow it to spin freely. What you do is you transfer magnetic properties, and once you allow it to spin freely, it will generally align with the direction that the ancients realized was magnetic north. And they were able to refine this discovery into the first magnetic compasses. And this is huge. The reason that this is huge is because this allows them, in lieu of complicated astronomical observations that can only be taken during the nighttime, to take their map and orient it with a magnetic dry compass. And this means that they no longer need to travel along the coast where they have readily recognizable landmarks, but can actually go out into the open ocean where it's much faster to navigate and get a pretty accurate bearing on where they are. So while we were able to readily apply the observations of magnets into magnetic compasses, we still were not able to quite figure out what made these magnets tick. So while they, by the 1200s, the 1300s, had magnetic compasses, in ancient Greece, they still didn't really know what made these magnets tick. Because here you have this stone, and it's not really, doesn't look living to you. Nothing about you tells you that this is gonna move. Nothing about this other stone tells you that it's gonna move. But when you bring these two things together, guess what? They move. They attract each other. And this was really baffling to the Greeks. In particular, to Greek philosophers Aristotle and Thales, because both of them associated movement with the idea of a soul. They saw living things as moving, and living things had souls. So, they thought there must be a soul inside the stone. And that's why we give them the honor of naming magnetism after Magnesia, which is a place in Greece with which they associated lodestones. Not actually, though. Alright, so the history of the name magnetism actually involves the fact that in the 1800s, when Ørsted and Ampere and other scientists were documenting magnetic phenomena and studying them more readily, that they needed a name which they could commonly refer to in papers that were later exchanged. And the name that they came up with was magnetism, because they recognized that the Greeks had documented similar phenomena with magnets that they associated with magnesia, because that's where they found their lodestones. But it's important to also note and give credit to the fact that lodestones were also present in other parts of the world, such as India and China, and that the people there also made observations similar to the ones that the ancients made, similar to the ones that we just made, and they designed devices that we would even recognize as compasses as well. So with that being said, and even with the advent of modern scientific methods, it still took us a little bit of time to figure out what was really making these magnets tick. Because, in fact, it turns out we needed to better understand electricity. We need to move past electrostatics to we need to move past charge just being there, and we need to start moving into charge moving. No pun intended, seriously. But, and really why this is important is because we needed galvanic pile batteries. Galvanic pile batteries allow us to run direct amounts of current through a wire. And in 1819, this led to the observation of Danish physicist Hans Christian Ørsted. And what Ørsted was doing is he was setting up a demo, which I've set up something similar here, where he ran current through a wire, and when he ran current through that wire, he noticed that it deflected a magnetic needle. I'm sorry if this isn't very visible, I tried my best, but there's also a lot of other good videos on YouTube that I'd encourage you to try looking up. But essentially, when I run current through this wire, it's going to deflect this needle. And now, this is really perplexing though, because here you have these two phenomena, which you thought might have been related, but Ørsted is actually going and he's finding a very clear concrete connection, one that we can still observe here, between magnetism and currents. And he wrote about these results. He wrote about these results, and a French mathematician and physicist named Jean-André Marie Ampere was really fascinated by these observations. He was fascinated by these observations because he knew that, well, here's what I'm thinking. He saw that magnetic needles typically interact with magnets, right? But now he's reading about Ørsted's results, and now magnetic needles are not just interacting with magnets, but they're interacting with wires, with current. So in some sense, that wire with current is acting as if it was a magnet. And he knew that magnets attracted magnets. So could he get a wire with current to attract another wire with current? And he set up a device, he went into his lab, and he absolutely found that that was the case. He found that when he set up current going in the same direction in two parallel wires, that they would end up attracting each other, and that when he set up current in two wires going in opposite directions, that they would end up repelling each other. And moreover, when two wires were crossing currents, in a sense, that they would actually twist each other so that their currents line up. And this is huge, because now we start having an idea of what might be going on inside these magnets. See, what Ampere was thinking was that he knew about electrons, he knew about the way that they circled around atoms, and he thought that the way in which electrons traveled could be thought of as a current loop, and that a current loop would have magnetic properties, and if enough of these electron current loops lined up, that you'd start to see a big-scale magnetic effect. And this was his theory on how magnets worked. Unfortunately, it turned out not to be true. There's actually a complicated mix of chemical geometry, crystal structure, and quantum mechanics that ends up playing into how magnets work, or at least how we currently understand how they work. And there's a great Veritasium video that I will link in the description. What's really important to know, because this is the first time that we get to look inside this magnet and we get to start thinking about what might be making it magnetic, what might be making it tick. The thing that's eluded us for hundreds of years. And this is the first time we get a look inside of it. And Peter did a lot of other experiments with current, with electricity, which is why we're going to talk a lot more about him later. And on top of that, because of his obsession with current, we actually even give him the honor of having his own unit, the amp, which you might recognize as coulombs per second, or the unit for current. And next video, we'll be talking about how Ampere's observations actually relate to special relativity with our modern understanding of physics. And as always, guys, thanks for watching. Please feel free to tell me what you think down in the comments. If there's any slight gaffes that I might have made in this video, please feel free to correct them so other people know. And if there's anything else that you think might be interesting, please feel free to leave a suggestion. And stay tuned for other videos. Thank you.